I need to know what type of econometrics and statistics background you have, because there might be still a mismatch. I am prepared to deliver this type of thing to an audience who are mostly PhD students
नहीं sir,
or young faculty.
they are MBA students.
Oh, okay, okay. But again, like, what type of background they have? I mean, do they have econometrics in your MBA course?
No, sir.
No.
Some have common factors.
Oh, okay. And anybody who is not an MBA student? Okay. So it looks like that I don't know, how effective I'll be, because I'm pitching, quite high, and this is all about econometrics. So again, if you don't know econometrics, I'll try to do my best. But again, this is talking about the techniques, and the techniques is based on econometrics. So again, as I said, without describing the technique, I'll try my best to give you an idea. And again, if you are not, if you still have doubts, raise your hand. That way, I know that I need to, talk it out in a different way, without focusing on the math, that part. Yeah. Okay. Oh, it's not audible from the back? Okay. Where does it go? I thought I talk so loud that people will get a headache if I wear a microphone, but it's supposed to be like this.
No.
Is it in better? So you are in charge. So I'm going to use my head the way you want. Okay, all ready?
Yes, sir.
Okay. So as I was saying, that what you raise your hand to give me an indication that I need to state it slightly differently. Okay. So I have never faced a situation like this. So to tell you the truth, so I'm not 100% sure whether I'll be able to do it the way I want. Okay. So again, as I was saying that I'm going to be talking about a tool that is primarily used for estimating performance. Let me go back to a different yes, okay, so again, as Professor Ramphal was talking about, that initially this project was, when we applied this to GIAN under the title managerial efficiency and productivity. I think one of the reviewers were saying that, okay, this is all about efficiency or productivity using econometrics. How about managerial efficiency? But I will just talk about it in a couple of slides. That what you learn as managerial efficiency is nothing but what we call technical efficiency. There is basically no difference between the two. Okay. So again, I just said that, well, the second point is, what is the link? Well, I mean, it's all about resource allocation. Okay. So in economics, you know that, well, the main thing that we focus on is, given the resources, whether you are using it in an optimal fashion. Okay. So again, managerial efficiency is defined in this way. That means you are maximizing what the managers are supposed to maximize output given inputs. So that's managerial efficiency. In stochastic frontier, we call it technical efficiency. That is, given the inputs, whether your output is maximized or not. If not, we just say that there is a slack. Okay, that is, slack means there is a potential for increasing your efficiency. Okay, so I can give you lots of examples. Let's say, well, you're taking an exam and you get 90 out of 100. So that what we say, that there is a slack of 10 points, right? That means there is a potential for you to increase your score from 90 to 100. Whether you will be able to do it or not, that's a kind of a different thing. But you can just say that technically speaking, or theoretically speaking, there is a gap of 10 points which you can bridge by studying hard or that type of thing. Okay. So the point is that, okay, how do I know how you are doing in a class? So let's say, well, I'm looking at the exam score, okay, and then I want to judge again like the students in the class, okay, so their performance again based on the scores that they have. So some might be getting 98, some 90. So again, if it is like this, then I know that the person who is getting 98 is the best, right? But that person might still have, because in 98 not 100, there is still a gap, right? So there are two ways of looking at efficiency. One is absolute. That means you are comparing with the best meaning 100% efficient, and the other one is relative. Then the 98 is the highest score, right? So when I'm grading individual, I'll be looking at what you call relative performance. How do you compare or with the best student in the class? So that's kind of the relative performance. Okay. So that the point is that we need a benchmark, right? To tell you how you are doing. Okay. Then you need to say that you compare to what or whom. So then I said compared to the best person in the class, and the best person might have a score of 98. Okay. So this is what you call relative efficiency. That means you have to have a benchmark, and in this case, the benchmark is the guy who got 98. Okay. But again, the benchmark it can be defined as also something like 100 points, although nobody is getting 100. But we know that that's kind of the absolute maximum, so we can think in terms of comparing individuals in the class, compared to again the absolute maximum. Okay. So that is kind of a benchmark. Now the point is that again, why are we interested in benchmarking? Well, benchmarking gives you a lot of information. As I mentioned that it gives you an information regarding where you stand in the class. Now after the exam, students always come to me and say, well, can you tell me where I stand? What does it mean? That means the person wants to know relative ranking of him or her in the class. Okay? And again, in order to answer that question, I need to know what is the maximum. That means I know the maximum is 100 points, and then I just say, well, how much did you get? If the person is saying that, well, he or she is getting 60, then I can just say, well, this is where you stand. Okay? So this is basically, again, given the benchmark, you are comparing individual relative to the benchmark. Now again, if you look at other examples, like most of the time we look at companies or firms or agricultural firms, their productivity, given the resources that they are using, and knowing that how far they are lagging behind, we can provide some sort of guidance to them. That well, look, you have a potential to increase your output, and then again, like next question would be, how do they improve? So we'll be talking about figuring out whether there is a slack, meaning a potential for improvement, and then the second point is that how can they bridge the gap between what they are actually producing with the maximum or the benchmark. Okay. So again, there are, I'm just moving faster than looking at every point of the slide. Is that again, like efficient management? If you look at this one, efficient management ensures that resources, and resources by that you can talk about human resources, okay, or financial resources, material resources are allocated efficiently. So again, like in the literature that I work with, the stochastic frontier, we call this allocative efficiency. So we use two terms, and again I will explain those things later on. One is for technical, then is technically whether you are producing the maximum possible, and then the second thing is that well, whether the resources are being used in an optimal fashion. Okay, and again optimality can be defined in terms of profit maximization or cost minimization or that type of economic behavior. Okay. Now, one thing, am I talking too fast?
No, sir.
Okay, because that's kind of even here this would be not a problem because you all speak English, but in other countries I always say that well, you are speaking too fast. Okay, now coming back to this, defining the benchmark. There are several ways of defining the benchmark. The two popular approaches that are used in the literature, one is stochastic frontier, again like this is my area of research, and the other one is called data development analysis, this DEA, okay. So the first one is stochastic frontier is what we call econometric approach, and the other one is programming. That means you don't need to know econometrics. There are some programming tools that are used to figure out even like the benchmark. Remember, the issue is exactly the same. Everybody is interested in knowing efficiency of the individual farms or individual producers or individual companies. But the difference is the way by which the benchmark is constructed. Because the benchmark is not developed. You have to construct the benchmark using the information. Okay? Information meaning that, well, I'm just talking about this exam score, that's kind of the information. If you give me the exam score, then I can come up with a benchmark. Okay? And the DA people will be using a different tool to define the benchmark, and again, like SFA people will be using a different technique. So the difference is in the tool that is being used to construct the benchmark. Okay? But other than that, if you think about, is there any big difference between the two approaches? The answer is no. I mean, everybody is interested in defining the benchmark, and therefore efficiency or inefficiency of each individual, and the difference is in the tool or the technique that is being used to define it. Now, briefly speaking, what is the main difference between the two? Now, the DEA, again, like if you look at the time period, DEA started in 1978 and SFA started in 1977. So they are basically, if you think in terms of the date of birth, they are pretty close to each other. Okay. So in DEA, the point is that, well, they talk about the relationship between output and inputs, for example, but they don't recognize any noise. So Professor Ramphal was talking about, again, in econometrics, whenever you do econometrics, there has to be an error term. Okay, so that captures many things. Okay, so we believe that no matter what the relationship that you are trying to estimate, that it cannot be exact, because we are dealing with, especially in economics or social science, we are dealing with some issues that cannot be in a defined exact fashion, no matter what you do. Okay, so we always allow some possibility of something that is unexplained, and that is included in the error term. Okay, in an econometric model. In DEA, there is no such thing. So they believe that the relationship is exact. Okay, so that's kind of the main difference. Okay? So personally, since I don't do that, I always say that, well, I don't like it because I don't believe that the relationship can be captured in an exact fashion. But that's what they do, and DEA is used widely. It's not only in economics, but people in operation research, management, engineering, they all use DEA. So the area of DEA applications is a lot more wide than SFA. And again, this SFA, stochastic frontier, some people like you might be also saying that, well, that's econometric, and if I don't do econometrics, I cannot use it. Whereas DEA, you can use it without knowing any econometrics at all. Okay. Okay, some people try to combine, again, like DEA with SFA. Okay, so sometimes they do DEA to find out the scores. Again, they compare it to the benchmark. Or DEA will tell you where you stand. Okay, and then again you try to figure out, whether again you have a gap of 10 points, how can you bridge the gap? So then if I just say that, well, you study more, or you work with some of your friends who are better than you, then those are some of the variables that can bridge the gap. Okay, so DEA people again try to combine those. That is, first they get the DEA scores, and then they run a regression. DEA scores on some other variables that can explain the gap. Okay, so that's quite popular. Okay, in SFA we don't do things like that. We do everything at the same time. Okay, so I will talk about those things at some point later on. Okay, so now let me just go back to the slide that I was showing you before, not that one. Okay, so I just talk about what is performance. Okay, now this is a joke that people often one of my friend used to make just to explain that why we need benchmarking. So look at this. Mr. A is asking Mr. B, how is your wife? And the answer is that relative to what? Right? So because you can say that, well, how are you doing? That question, if you think about it carefully, it is not a question, or a question that does not have a definite answer. You will say that, well, fine, but again, do you mean fine relative to something? So this is the point, is that, well, we have to define a benchmark, okay, so that you can answer that, well, yeah, I'm doing fine because I am, so if I ask a student, how are you doing in the exam, he says fine, because he or she might be getting 98 out of 100, so then again, it's a definite measure of what he or she means by being fine, okay. So this is again like the reason why benchmark is important. Now for the rest of it, what I'll be doing is the examples. I was giving you many different examples, and I may continue doing those. But I'll be focusing mostly on production function. That means the relationship between inputs and outputs. I guess you all know what a production function is, right? Because in MBA courses you must have taken in microeconomics, right? No? So microeconomics meaning you must have seen a production function, right? Okay. Yes? It has to be. If you say no, I don't think that I would be buying your argument, because this is so fundamental. I mean, okay. So I'll be talking about again like production function. So the idea is like this. That means you have an outcome variable y, but again, like if you are not thinking in terms of production function, I can still expand that by giving you a different example. So what is the outcome variable? I mean, in Ramphul's lecture, he was talking about cells as the dependent variable, right? I mean, was it cells on the dependent variable, and then advertisement on the right hand side, right? So that type of thing. So y is the outcome variable, and again x is the variable that is affecting your y. Okay, so again you can think in terms of sales and advertisement or some other things. So there is a relationship between y and x, and we can write it in mathematically. Y is a function of x. Right? So that f of x can be linear, can be nonlinear, can be anything, right? So it's kind of a function of relationship between the two variables. And again, like if you write it like this without anything else, then we just say that the relationship is deterministic, meaning that there is no stochastic or random component in there. Y is an exact function of x. Okay. So if it is linear and if I write y equal to 2 plus 3x, I know that again like this is a straight line. Okay. But again, if I add an error term to it, it's and the error term has 0 mean, then again like on average it's a straight line, but individually you might be deviating from the straight line. Okay, so again like in this framework, we just said that, well, I mean if this is a production function relationship, then we just say that what is this? This is that means if x is a vector of inputs and y is output, then again this relationship tells you the maximum output given your x. Okay. Now the question is it in reality, if you're looking at things, do you think that while it's possible to get to this maximum value of y always, or some people might be able to not able to produce the maximum possible output? Okay, so let me do it like this. Okay, or maybe I'll come back to that one. because I have a different example before I go to the production function, and that might be useful for you because some of you, I mean, you have to be comfortable, but let's say that you are looking at the ranking of the universities, okay? And your Y is the rank of the university, and you might be relying on the rank based on the salary of the people who are getting out of the university, okay? What is their average salary, okay? And X is some other variable. So the question is, in reality, since the ranking is not exactly the same, that means we agree that some universities are not ranked as high as, let's say, the MBU, right? Or there may be some other universities which are ranked in higher than MBU, right? So then again, if Y is the maximum, Y is the actual rank, and f of x is the maximum, then we can always say that the relationship between Y and X is like this. Y is less than f of x. F of x is the maximum, that means the possible rank, and then again Y is the actual one. So Y is less than equal to f of x. So you can think in terms of taking the ratio Y over f of x is the performance measure. So Y over f of x is going to be always less than or equal to 1 or 100%. Okay, this is actual and this is the maximum possible. Your actual cannot be bigger than the maximum, right? So when you take the ratio, it has to be by definition less than 1. Okay, at the most, now it would be going to be equal to 1. Okay, so again, like when you look at the performance measure, we'll be looking at Y over f of x. Sometimes we use the word inefficiency. So what is inefficiency? It's basically 1 minus your efficiency. So if your efficiency Y over f of x is 0.9 or you are 90% efficient, then we say that well, you are 10% inefficient. So we use the relationship. Sometimes we use the word inefficiency, sometimes we use the word efficiency. But efficiency is again like between 0 and 1, whereas inefficiency is 1 minus efficiency. Okay. So again, let's just look at this example of college ranking. So this magazine Economist, published a ranking of the universities, mostly in the U.S. Okay, and U.S. Universities, especially the deans, okay, pay very close attention to the ranking because it's kind of, I mean, it's not related to the prestige of the university, but they want to put some emphasis saying that okay, ranking of our university is let's say what we are ranked top 90%. Okay, so this is kind of an advertisement on the part of the college for the prospective students. Okay, so for example, if Harvard is ranked not 100%, but 70%, still people will go to Harvard because of different things. Okay, so let's say well you want to look at a rank. So the way you just look at it, so these are the actual points, and I just said well Y is just well this average salary of the people who are graduating from the university. Okay, and your X is let's say that X is let me just see whether I have this X variable in the list. No, it's just not. So you have the data on average salary with let's say 1 year of experience and that type of thing. So you get different data points like this, okay, for corresponding to different universities, and you just draw a line like that. That means this is a fitted line that Ramphal was talking about. So then again, what happens when you compare a particular point with this line and you are above this, then what you just say that okay, you are better than the average, right? So you are buying a product and again you're paying a price. Let's say we're using Amazon, the price is lower than the other price that you can buy in the local market. So then what do you say? We just say, well, you get a deal, good deal, right? So again, good deal in terms of efficiency is that okay, you are better. So in this particular case, the college is better than the average if the actual point is above the line. And how do you do that? Or you feed a line and take the difference between the actual and the feeded value. So what Ramphul was talking about, your S minus S hat is the feeded value and actual value is integer. So again, if it is positive, then you know that your college is doing better than average, right? Similarly, if you're below, then your college is not doing as well or doing worse than the average. Okay. Now the question is that, well, you can do this type of thing, but claiming that, well, this distance in here is indicating efficiency of the college or inefficiency of the college might not be a good idea, because this is affected by noise. Okay. So when you are fitting a line, you are assuming that, well, y and x is related in this particular linear relationship. Okay. So again, you may have the relationship nonlinear, you can have other variables explaining your y, so there are a lot of things. So what we need to do is we need to separate the residual or separate even the residual. The whole thing is not a measure of efficiency. It might be affected by the noise. You cannot, or you are not able to separate noise from inefficiency. You are getting a good deal, we just said, well, you are better than others, right? Or your college is better than others. It may be a fluke, right? It happens suddenly in 1 year, right? But the question is that, well, whether that will be repeated in every year or not. So the question is whether it is affected by any noise term or not. So we need to say that, well, again, or measure your efficiency related to the benchmark, taking into account the noise term. So this is the main departure from DEA. We allow the possibility that the relationship, no matter what, can be affected by the noise term. And we need to, when we measure efficiency, we have to take into account this noise term. Okay, so how do you do that? Well, that brings us to stochastic frontier model. So what we do is we write it like this. So here I put log, ln is log, but you can think in terms of this as y, because this is a log of your output, and then f of x is kind of a function of x, which are inputs, mostly in log, and v is the noise term, and u is inefficiency. Okay, so then again, we want to say that, well, the frontier part is this f of x plus v. Then this is not the deterministic part, but also the stochastic part. So we want to measure inefficiency of a firm or an individual relative to the stochastic frontier, because we want to say that, well, the difference between y and f of x in log, or the ratio of y over f of x, is not entirely efficiency. It might be contaminated by noise. Okay, so we want to factor out the noise term from inefficiency. So that's why we are adding a v term, which is the noise, which is what in Ramphul's model he was writing it. But again, we are adding something which is u, and again we are putting a negative sign, because inefficiency will be lowering your output. Okay. Okay. So now let me just get to this production function a bit more, and again, I won't go into the. I think these are available or made available to you. So the production function, because I'll be coming back to that, but again, your next few slides, I'm defining what a production function is. So again, so this is kind of textbook definition. So you have a vector of inputs, you have capital, labor, material. Again, in agriculture, you have land, labor, seed, fertilizer, and all sorts of things that is used to produce some output. And this may be, like wheat, or again, cauliflower, or tomatoes, or things like that. Okay. So this Y is the output in terms of a single product, and again, these are the inputs that are used in the production of that good. Okay. So this is what we mean by a production function, and these are some properties. The thing is that, well, if you use more X, then you are going to be getting more output. Okay, if you don't use any input, then your output is going to be 0 and that type of thing. Okay. And again, this is a mathematical property, it's continuous, but again, let's get rid of all those things, because one other thing that is important for us is measuring returns to scale. So what is returns to scale? Then let's just start with a particular farmer. For example, he or she is using certain amount of land, using some fertilizer, and some people are going to produce wheat. Now the conceptual issue is what would happen to his output if he increases everything by, let's say, doubles everything. So land is doubled, labor is doubled, fertilizer is doubled. Okay, what will happen to output? Do you think output is going to be doubled? Okay, some will say that yes, output will be doubled. So if your output is doubled, then we will just say that returns to scale. You are changing the scale. Scale meaning that just like going to a copy machine. Just you put the button that you increase the size of it by 50%. That is, the scale is increased by 50%. Right? So what would be happening in here with the output? So if output responds exactly the same percentage, then we say that returns to scale is constant. If it responds less than that, then we just say that there is decreasing returns to scale. If the change in output is more, then we just say that it is increasing returns to scale. So the returns to scale is defined as, again, the percentage change in output due to a percentage change in all the inputs. Okay? And if the percentage is exactly the same, then is CRS, constant returns to scale. Okay? Otherwise, it's either decreasing or increasing, because we want to estimate whether it's increasing, decreasing, or constant returns to scale. So mathematically, given the production function f of x, returns to scale is defined in this way. Okay? So you take a derivative of y, or log y, with respect to each of these x's. Okay? So you all know derivative or partial derivative, right? You cannot say that we don't know. So if I define a production function or give a production function, you can take a derivative with respect to log of x, and then for each x, and then sum them up. That would be giving you a measure of returns to scale. Okay, so here is an example. So this is what we call Cobb-Douglas. I guess you all know that. So Cobb-Douglas production function. So before log, the production function is going to be written like this. So your y is equal to, for example, a, and then x k. Let me just do it like this. See the advantage of having this thing. K to the power alpha, L to the power beta. Think in terms of only two inputs, A and L. Okay. So then again, you can take a log of that. So log of y is equal to log of A plus alpha log of K plus beta log of L. So then again, taking a derivative of this with respect to K is what? That is alpha. And taking a derivative with respect to L is beta, right? So then again, del log y, del log L is equal to beta. And then again, if you take a sum of those things, so alpha plus beta is a measure of returns to scale. So alpha plus beta can be less than 1, can be equal to 1, can be bigger than 1. Right? So we are not imposing any constraint on them. We are estimating them from data. Okay, so like what Ramphul was talking about, that is given data you can estimate those things. And again, like I mean, if you have never seen a linear regression or know how to run a regression, and this is quite simple. Give the data. I mean, you are all familiar with Excel. Even Excel can do this thing. So read the dependent variable y and all the independent variable. All right, and then again, like just run the regression. Is it okay? Okay, so that's kind of a returns to scale. Now, let's just get to efficiency. So the production function, we usually graph it like this, relationship between y and x. So think in terms of this relationship in terms of only one x. Is there any issue?
Yes.
Okay. Um, so again, like, you can have two inputs, but again, you hold one input x2 as unchanged. So let me use the highlighter. So your x2 is unchanged, and this is a relationship between y and x1. Okay. So this is the shape of the production function. Now again, given x equal to x1, what is the maximum? Maximum is given by the point B, right? But what happens if you are producing in here? You are using this much of input, but your output is less. What is happening here? Okay. Maximum? Do you know how to produce less than maximum? Yes, we all know, right? You don't work as hard as you are supposed to be, right? To get to this one, this is the maximum, right? So again, producing less than maximum is always possible. So let's say well, somebody is producing at this, but using this much of input. So you know this person is clearly inefficient. Now the question is, how do we measure efficiency or inefficiency? So remember I was talking about slack. So what is this difference? This is the maximum, this is what your actual score. Remember in the exam score I was talking about? So what is this gap? Is it telling you that what this shortfall? Output shortfall in terms of output, in terms of score, again, you just said, well, what is the potential for improving your score, right? So this is the measure that you can get by moving up, okay? Now you can also go to the frontier instead of moving up, going this way. What does that mean? If you go this way, you are producing the actual output which is observed using what? You are using this much x, now you are using this. So remember that Professor Ramphul was talking about this is in the context of agriculture. Okay, so you are using like let's say 10 people, right? But you need actually 8. Right? So what are those 2 people are doing? Well, they are working in there, but you know that some are smoking and some are chatting. I observe those things because I work on this type of thing. So when I let's say was driving or somebody is driving me, I just look around and see how many people are working and how many people are chatting and how many people are smoking. Right? So then I just say, well, this is kind of an indication that everybody is not working, meaning that there is a gap. Okay, I don't think that they are allowed to smoke or there is a smoking time, but they are doing it anyway. So that means again like there is a lot more people working in there than what you need. In the past I did some work on Indian banking. And since I have personal experience with Indian banking, so you go to a bank and you see that there are so many people working in there. And then you can clearly eliminate a lot of them. Why you are not doing that? Because most of the banks are personalized, right? So the government is saying that, okay, they're saying that go and hire people even though the bank does not need any more people. Okay. Sometimes I go to a store, and this is somewhat, again, my personal experience. I just went to a store and I see that there are salesperson everywhere, and they're chatting with themselves. And I'm going in there and I'm asking, what is this product? He said, well, okay, aisle number 6. And I said, well, what is aisle number 6? And I turn around. So they're supposed to be taking me to aisle number 6 and pointing out the product, because there are so many people in there, but they're chatting with themselves. So this is kind of an indication that, again, resources, meaning human resources in there, are not efficiently used. Right? So you'll see those type of things everywhere. And since, again, it's not that well I do research on those things by what I observe, and I just see that, again, if I want to give an example, then what sort of example I can give. And again, one time I was in Tokyo. So then I noticed that after getting out of the plane, you have to take a bus because the city is quite far from the airport. So I was instructed that take bus number 3, for example. So I was just standing in there, everybody queues in there, so Japan, right? And then I just saw that the bus comes and stops. This is a kind of mini bus, small bus. and there is somebody, I don't think it was a driver, somebody was taking the bag and putting it there. And you know the way he was putting the bag, it's just like the way you would put your own bag. Meaning that, well, not like in the US, you just take the bag and throw it inside. Okay? So he's just holding it like this and gently putting it down. I observed it, and again I gave a seminar. Afterwards, so I gave that point that, well, look, this is how they do things in Japan. And when we were talking about again like efficiency in the use of resources or labor, you can see that that immediately the bus comes, immediately this guy comes from nowhere. I did say him before, and then he just started packing those things. Right? So you observe many different things again like the way things are done. So one is what we call, this one is output oriented, because this is measured in terms of output shortfall, okay? And this is called input oriented, because this is related to input overuse, right? You can think of inputs here X as resources, right? So the question is that, so the question is whether the resources that you are used can be cut down without cutting down production. And this is happening all the time. And again, another example is that we always argue that, for example, a country is poor because the resources are not enough, right? So in development economics, the course I took many years ago in India, this one, India is poor because we don't have enough resources. But now I argue that, well, yeah, I agree that resources are not enough. But the point is that again, whatever resources you have, are you using that in an efficient way? That is my question. And what is your answer? Do you think that resources are used in an efficient way? No.
No.
You get money from the central government. How much of that money is being used? Okay, so you all know that on the way coming from Delhi to even in here, it started long distance. Something is just getting on the way. That means this is resources are being leaked. Leaked meaning that somebody is taking some part of it. Maybe you are granted in 5 lakhs, but 1 lakh goes to the people who are working in that agency, and then again ultimately the amount that you get maybe 70% or 60% of it. Okay. So the point is that, well, it's just not the resource scarcity. Okay. The point that I would like to emphasize is that, well, I would like to see whether the resources are optimally used. Okay. So another case, since I'm just talking about this thing, because again, like a technical side, I won't go into the details. So again, think in terms of using data to see that which states in India, okay, are doing well. So think in terms of GDP, okay, and then again, like think in terms of infrastructure, capital, labor, and that type of thing, estimated production function, and then you rank the states, okay. I don't know which state will be ranked first, but again, like this is, I don't want to talk about the state level, but again, this is something that people do talk about. The other day I was looking at a newspaper and they were saying that, well, Bihar, we're supposed to say that, well, Bihar is economically worst, right? But now I say that, well, Bihar is taking taking the lead, and in terms of your IAS, IPS, and those type of exams, Bihar is not lagging behind. So the point is that you can always do this type of thing, and then if you have a time series data, you can just see what is happening to efficiency over time. Okay, you don't say that, well, Bihar is really backward. Well, it was backward 20 years ago or 30 years ago, but the question is it still backward, right? And again, when you say backward, relative to what? Okay, so I said that, well, if you do a frontier type thing, and then in the rank, Bihar would be in the lowest rank 30 years ago, but now it's not the lowest one. So this is kind of usefulness of this type of studies. So you need to get data on whatever level you have, either state level or again the municipality level or district level, and then again like you do a comparison. You feed benchmark, and then you compare every observation related to the benchmark. Right? So there are tons of things. The type of things that I do are not in the aggregate level. I tend to work with the individual data using micro data. So using farmers, for example, I don't have data from India. I use data from Norway because I have some co-authors from Norway, and they have also farm level data. But again, like if you can get farm level data in India, I know that there such data sets are available. But since I don't have the connection in India, I don't work with it. I have nothing against working with Indian data, but somebody has to get the data. Okay. So again, a friend of mine who works with Indian data, because he knows people. Okay, not only getting data but also professors with whom he works, and I don't have that many people I know in India with whom I want to work. So again, given the data, I mean, if you can collect some data, then or you can use this type of benchmarking exercise to again compare the states, how the state is progressing over time. Okay, that would be kind of an interesting thing to study, because as I said, well, I know that again people just say, well, Bihar is Bihar. I mean, nobody wants to talk about it because it's so bad. I think the joke was that at some point, this is really a joke, that Pakistan was thinking in terms of taking over, say that well, to India, that we want Kashmir, in the whole Kashmir. And in there was the prime minister says, okay, no problem, we'll give you whole Kashmir, but you have to take Bihar also. No. So I said, no. That was the end of that. So this is the kind of the joke, to just say that this is a joke literally, to say that well, Bihar was so backward that nobody wants to be associated with Bihar. But now again, it's a different case study. So again, the interesting point is just to see how the state is improving, and how, for example, West Bengal, okay, was claiming West Bengal was claiming, or Bengalis will claim that well, we are in the top, but it's nowhere in the top. I know, because I come to Calcutta pretty much every year, and I see how things are going down instead of improving. Right? So this would be kind of an interesting study to do. Okay, so now again mathematically, when you just look at this graph, okay, so 20 minutes you said that, so again, so basically I'll stop what, at 5, or whenever it says that. Okay, so this is the graph. It says that while you have output shortfall is given by the maximum and the actual, and this is the input overuse. So the question is mathematically, how do you capture this? Okay. So again, like if it is input oriented, you can do it like this. So y equal to f of x, and then you multiply by a factor which is less than 1. Please remember, if this is 10 and you know that you can produce the output with 8, so you have to multiply 10 by a scaling factor that's less than 1, right? So 10, and then again I multiply by a factor to make it 8, right? So what you do is you multiply by 8 over 10. So that is a point 8. So this e to the power eta is the such factor. So eta is positive number. So e to the power negative number is less than 1. So we just do it like this. Okay? And we do e or exponential because we take a log, and that will make it linear. So that's kind of the reason why we're taking exponential function. Okay? And then for so the input oriented inefficiency is like this. So for output oriented, we write like this: y equal to y star. Y star is the maximum possible output. That's f of x. Remember that point, big B, and on the top of the line. And then again, like if you are inefficient, you are producing less than that. So your y star multiplied by a similar factor, and this is less than 1. So again, u is being positive, and e to the power minus u, meaning that well, this is less than 1. So you are multiplying by a factor that is less than 1 to make it equal. So So basically what would happen is that you had y less than y star. So the question is that you have less than, how do you make it equal? How do you convert the inequality sign to inequality sign? Well, I mean, this right hand side is less, so I mean bigger, because again y is less than y star. In other words, y star is bigger than y. So what you do is you just scale y star down. Okay, this is heavier than this, and that's why we are just multiplying by e to the power minus u, which is less than 1, to make it equal. So if something is, you have two sides, one side is bigger than other, you can make them equal by what? Adding something or subtracting something. But instead of adding and subtracting, here I'm doing multiplying by something, okay, because again I'll be taking log. So that when you have multiplicative sign taking log, meaning that it becomes additive. Okay. So then again, you just write it out, y is equal to what is that highlighted? So y is equal to f of x, this is the frontier part, and then e to the power minus u is that this efficiency. So e to the power u, meaning that efficiency is never going to be greater than 1. So if it is less than 1, then again you write it this way to make it equal by taking log. So I'm just doing it like this. So what is u or minus u? This is a measure of inefficiency. Okay. And so what we will be interested in is estimated u. Okay. Okay, so this is again this is the part that we have so far, and then again what is this f of x? Now this can be represented by a parametric function. You can think in terms of this Jacob-Douglas or translog. I am not sure whether you have heard the word translog, probably not, but again this is kind of a second order approximation. So let's just think in terms of Jacob-Douglas, which is linear in log, right? So you can say that well, this is linear in x, and then again this is u, which is one-sided, meaning that a positive number. Now remember, at one point I was talking about noise term. That means you cannot talk about the discrepancy without introducing noise. So the stochastic frontier that was introduced in 1977, where basically argues or makes that point, that the relationship that you are trying to estimate, okay, will have noise in it. So when you are writing it like this, okay, you have to, so when you are writing like this, let's say log of y is equal to log of so let's say log of f of x minus u, and again there is no noise. So the idea is that well, you have to add noise, and stochastic frontier does that. So what you are doing is, you see that we have now added a noise term, v in there. So you have u in there, and then you have v. So u is inefficiency and v is noise. So the question is that the regression that Professor Ramphal was showing, we had one error term, v, right? But now you have two error terms. One is v, the other one is u. So this is the most challenging part. That means how do you separate? We don't observe that, right? Nothing is observed other than y and x. So the question is that you are trying to estimate a relationship, okay, and again eventually get a measure of u without observing them or without separating u from v. You can run a regression and get a composite measure of v and u. But the question is that how do you separate u from v? And if I'm drinking tea or coffee, and then I said, well, milk is added. Now how do I'm drinking it and I see that, well, milk is added, but can I take the milk out? Okay, so this is something like that. We are seeing these two things together, but ultimately we want to, get an estimate of u, meaning that we have to separate u from v. And that's what we do in stochastic frontier. So how do you do it? Well, we introduced distribution assumption. So So this is where the technical edge starts. Okay, that means the way you can separate U from V, okay, by using some distribution assumption. And what do you mean by distribution assumption? Certain things you know or you have heard. So if I just say, well, V is normal, everybody knows normal distribution, right? I mean, doesn't matter whether you have taken a course or not. Normal distribution, or in the US, everybody knows what a bell curve is, right? So that's the normal distribution. Okay. So if you draw if I do it something like this, so this is a normal distribution. Okay. So it goes from minus infinity to plus infinity, and again like you can have a geomean. So this is a bell curve or symmetric distribution. Okay, normal distribution. But what is U? U is positive, right? So you cannot be normal distribution. Normal distribution meaning that what you will have a negative value and positive value, right? Okay. So if it is a inefficiency one-sided, then it has to be something different. So what you do is you can just think in terms of a normal distribution like this, cut it in here, and then erase this part. Oops. If I look at this, then again, you can say, well, that's U, because U is taking only non-negative values. So this is normal, and this is something else, right? We just say, well, this is normal, and this is half normal. Why half normal? Any idea? I just took half of it, right? I took the other half out. I took the positive part of it because so now again we are mixing two things. One is the full normal and the other one is half of normal. So we are adding those two things. So if you're a statistician, you will be able to see that, well, okay, I know that one has a full normal, the other one is only half of it. So there must be some way to distinguish between them. And again, like, the technique that we'll be using is coming from statistics. So this is a mixture of a regular normal and a half normal, okay? Or sometimes we use the word truncated normal. A normal is truncated at 0, okay? Okay, so let's just take a break in here because as I was saying that even though it's in university, the time limit is 1 hour, so I don't understand. So I have to talk to these people that you cannot run an university with a time limit on this type of thing. Okay, so let's just take a break for 15 minutes or so. I don't know whether you can get coffee or tea. Okay, I think all those people are organizers are outside. So, is there any coffee for you guys or what? Or if there is no tea or coffee, just take a break. I mean, just because otherwise it's too much. Right? Okay, so let's just take a break for. Is there any coffee for them or break or?
So correct is break.
Okay, sir. Sir, it is request from our side that please.
More minute because I think we have a requirement in terms of time because they are recording everything which will go to the ministry. Okay, so I don't know how much your cost is higher because you are inefficient, by how much your profit is lower because you are inefficient. So if you are the manager, okay, you know that there is a potential to increase your profit or reduce your cost, okay, and you have to do something. So this is kind of a benchmarking will give you that idea. Otherwise, if somebody says that, well, okay, you are inefficient, you need to improve. You have no clue, right? And I mean, how to improve it or how much you can improve. So these are techniques that will tell you that, well, at least give you an idea that how much inefficient you are, what is the potential for improvement, and how you can improve it, provided that we know again, like the factors that can influence our efficiency. So then again, the point is that we have two terms U and V, and then the final model that we are looking at is like this. Log of y, for example, let me write one more line in here. Log of y is equal to xi beta plus vi minus ui. So we have subscript I because I'm not now talking about cross-sectional data. So data at a particular point in time. If you're looking at the companies, you are looking at the companies, okay, at a particular point in time. That's about 2024 or 2020, okay, or that type of thing. But then later on, I'll be talking about panel model, where we are looking at or observing the companies, each company over a certain number of time periods. So that would be a panel, okay. So then again, as I was saying, you have two terms in here. One is noise, B, and the other one is inefficiency. So that is just written as epsilon. Right? So the question is again, how do you estimate a model like this? And this is part is technical because what we do is we use something called maximum likelihood. Okay, so this is not like calculating using ordinary least square, which you have heard probably, but something that's different is maximum likelihood. So for maximum likelihood, you have to derive the density function of this. So this is how this is done. And then again, this has some plots of the abnormal distribution to illustrate the point that again, depending on the value of sigma square, the variance, again, like the percentage of firms close to 100% efficiency, meaning zero inefficiency, can be very high, can be very low, depending on how flat the curve is. Okay. And then again, this is the likelihood function, which you don't need to derive. But if you ever want to estimate this model in the SCADA, I think tomorrow at some point we'll be talking about how to use SCADA to estimate this type of model. So again, like you have SCADA in your computer, and you basically go and look at the command, and you just hit the button, and you'll get results. So you don't need to know all those things. Although again, when I go to a conference like this, I always tell people that you have to do this type of thing because if you rely everything on computer, then there is so much that you can do. You cannot do everything. You have to rely on the codes that are written by others. Okay. So anyway, so you do. So the likelihood, maximum likelihood, is a method of estimating, just like OLS. So what happens is, well, when you do maximum likelihood, instead of some other in R or some other packages, it will give you the estimate of the slope coefficients beta. It will give you the estimate of the variance of V, the noise term, and then the variance of U. Right? Okay, so these are the parameters of the model. But ultimately, our objective is to estimate U. Right? So again, like we are not getting U directly. We are getting the estimates of the parameters of U and V, and then again the beta coefficients, right? Or beta coefficient. So, and again, when you estimate those things, you can get epsilon, which is the difference between log of y minus this, log of x beta. But again, remember, this one has both milk and water, right? Or coffee. So the question is that, well, we need to separate U from V. So this is residual, which is this is V minus Q. So you get the composite measure. You just look at the coffee, right? The way they serve. But again, like you need to separate it from. I mean, if you want to get the milk, okay, and this is what it is. Then again, it's not that obvious, because if I give you the mixture, you cannot immediately figure out how much is milk or get the milk out of it, and then left the residual would be something else. So then again, what we do is that we borrow something from statistics, and we just say that, well, I mean, given the setup, okay, so the distribution of U condition on this has a truncated normal distribution, and we can take a look at the mean of U given epsilon. So this is not observed, but we can figure out what is the mean of U given the composite error. And there is a formula for this, and again, like if you use theta or R, it will give you this number. So this is going to be a measure of inefficiency. So let me just write it out. You had I is this. estimate of this. So there is a formula for this. So you can see that, well, I mean, I would be completely inoperative if I were right, right? So that's the reason why I said, well, it has to be done, because otherwise I'll be non-functional. Okay, so this is, again, like if you use R or STATA, you ask for this, okay? So the computer will give you the estimate of E for each individual observation. Okay, so that's kind of the good thing. So now again, going back to the example that I was giving you, that again we are looking at the scores, exam scores of a class, okay? And then again you can see that by how much they are behind their potential. So again, remember, this potential is not 100 necessarily. We are just saying that, okay, am I efficient? So I'm not comparing myself with you. This is not relative efficiency. I'm comparing myself with the potential that I have. So this is a very difficult thing, right? I mean, I remember that, well, my kids will be saying that, well, you are not happy with our performance. Why? Because I didn't say that. This is what I do. I said, well, I'm not comparing you with your friends who got a better score, but I'm comparing you with your potential. And I'm thinking that, well, you have not able to attain your potential. So again, this can be applied to me also. Have I reached my potential? I don't know. So this is kind of a tool that will help you to figure out this potential. So remember, this is not relative. Relative is comparing one with the other, which you can always do. If I know the individual scores, then I can compare you with him, right? Because you got 98, he got 97, so I can compare. But again, like without again making a comparison, I mean one with the other, this is a kind of an absolute measure. So maybe there is nobody who attains the maximum, right? But then again, so that's kind of a theoretical concept, abstract. And the way we are doing it, we are estimating it using data. So this benchmark is hypothetical. It's not observed. It's being constructed using econometric tools. Okay. Okay. So let's yeah. So let me see where natural stop. Yeah. So let's just stop in here, and then we'll start tomorrow at 9:30.
Yes, sir.
Yes, sir.
Okay. Right.
Yes, sir.
Okay.
Yes.
So thank you. You have to tolerate me for the next few days. There's no way out. But again, I'm pretty sure that while you learn something, even though you do not follow the math, and I'll try not to put too much math in there. I mean, I'll be saying that, well, this is how it's done, and again in the computer, and this is how this kind of person will be doing it. So tomorrow you'll see some of it.